Okay guys, this is our last example of improper integrals with infinite bounds. I think this one's kind of cool because this is what our region looks like. Isn't that beautiful? I've got the integral from 0 to infinity of this function. Turns out to be 0 when x is 0 and 0 when x is 4, and it goes below the x-axis for a while, and then it goes above the x-axis and has this beautiful curve. You've got mins, you've got maxes, you've got this beautiful horizontal asymptote. It's a very nice looking function. We want to know, is the net area under this curve finite or not? Now, you might be tempted in looking at this picture to split this into two integrals, one from 0 to 4 and one from 4 to infinity. Completely unnecessary. What we're going to do is the same thing that we did with all the other improper integrals of this type. First, we're going to write it as a limit. The problem occurs at infinity. This function is well defined everywhere for all real numbers, definitely for the interval from 0 to infinity. So this is only improper because of this upper bound being infinite, because the domain is unbounded when I look at this picture. So I'm going to write it as the integral from 0 to b. I'm going to take the limit of that integral as b goes to infinity. So maybe here is my b. Let's say that's b. And I just want to know what that that area is. And then I say, okay, well, what happens to that as b gets larger and larger and larger? So when I evaluate this integral, it's going to take care of this area minus this area. And then we're going to see, okay, does that area approach some finite number as b goes to infinity, as we keep stretching b to the far right? We let b equal 100, and b equal 1,000, and b equal 1,000,000. Does this approach a number? Let's find out. Okay, so as always, we wrote the improper integral as a limit. First step, that's good. Now the second step is to evaluate the antiderivative and apply the fundamental theorem of calculus. Okay, so I'm looking at my integral, looking at my integrand. Say, do I have a rule for that? Absolutely not. Can I do u sub? Well, I could let u equal x over 4, but the derivative of that negative x over 4 is negative 1/4, and that's not going to take care of this polynomial. So u sub is not the most efficient way of doing this, but we've studied integration by parts, and we know if we've got a polynomial times an exponential, or a polynomial times a sine or cosine, tabular integration is the way to go. So we're going to use tabular integration to evaluate this antiderivative. I put u over here, dv over here. U is my polynomial. Whenever you're doing tabular integration, you always want u to be the polynomial, and dv is everything else. Now I'm going to ignore the dx because that's what we always do when we do tabular. And then remember how this works. With tabular integration, you differentiate u. So you're going to differentiate in this column until you get a 0. So you're going to have 2x minus 4, derivative of that is 2, derivative of that is 0. And then in this column, you're going to anti-differentiate until you have as many entries in this column as you have in this column. We want the same number of rows. I've got 4 rows over here, 1, 2, 3, 4. I want 4 rows over here. So I anti-differentiate this. The antiderivative of e to the kx is e to the kx, we have to divide by the k, and k is negative 1/4. So we're dividing by negative 1/4. It's multiplying by the reciprocal because it's a fraction. So we're going to multiply by negative 4. So every time we anti-differentiate, we're going to multiply by negative 4 every time. Just keep doing that. So we multiply by negative 4 again, and we get 16. And we multiply by negative 4 again, and we get negative 64. And we've got a sign convention, not actually a convention, excuse me, it's just a pattern that we have to follow to get the right answer. Now remember how tabular works. The antiderivative of this is u times v. So you're going to multiply across, and then multiply by positive 1, and then add. And then you're going to multiply across, multiply that result by negative 1, and then add, and then multiply across the diagonal, multiply by positive 1, and then add. We've run out of diagonals, so we are done. Okay, so we have computed the antiderivative. I still need my limit in order for everything to actually be equal. The limit as b goes to infinity of this is equal to the limit as b goes to infinity of whatever we write down here. So I'm going to write down this product that we talked about. You multiply, factor out that constant. And then I add, multiply, and then I'm going to add this, but I'm also going to multiply by negative 1, so I'm going to subtract it. And then we multiply these two together, and then we add, evaluate this from x equals 0 to x equals b, and you want to take the limit as b goes to infinity. Now notice we've got exponentials everywhere. If this were an integration by parts problem, I would leave it alone, slap a plus c on it, and I would be done. But that's not what we're doing here. We need the area under the curve from 0 to b, and that means plugging in b, plugging in 0, and then taking this limit. So I'm going to do something I don't normally do with integration by parts. I'm going to simplify this first. And then once it's simplified, I'm going to take the limit. It's going to make taking the limit a little bit easier. So factor out, to simplify this, I'm going to factor out the e to the negative x over 4. So I'm going to factor it out this way. And then I'll leave everything else that's left here in parentheses. So distribute the negative 4 there, get negative 4x squared plus 16x. Distribute the negative 16 there, so we'll have negative 32x. Negative 16 times negative 4 is positive 64. I'm subtracting 128. And we evaluate from x equals 0 to x equals b and subtract. Of course, we can simplify further. I'm just doing algebra now, no big deal. 16 minus 32 is negative 16. 64 minus 128 is negative 64. Now let's finally do the fundamental theorem. I'm going to factor out the negative as well. Could factor out a negative 4. I'm just not going to do that. So we'll have negative 4x squared plus 16x plus 64 times e to the negative x over 4. I said I was going to do the fundamental theorem, but I didn't. I factored out a negative instead. Now I'm finally going to do the fundamental theorem. So replace x with b. And then replace x with 0 and subtract. Subtracting a negative is going to be adding. You don't have to add the zeros if you already know it's going to be 0. I'm just showing my work because I'm making a video for you guys and I want you to see all the steps, all of them. But as you're doing this, there's some steps you could probably skip. You can say, oh, that's 0 and that's 0 and that's going to be a 64. And I'm subtracting a negative, so it's going to be a positive 64. And that's an e to the 0, so that's a 1. So you could simplify all of this as you go in your head if you want to. Or you can show all your work like I did right here. E to the 0 is 1. Okay, so before I go any further, let's just talk about this guy right here. As b goes to infinity, that's a polynomial. It's a quadratic polynomial. This is the leading term. As b goes to infinity, b squared gets very large. And multiply it by 4, still very large. Multiply it by -4, it's going to be large and negative now. So this whole thing, if I include the negative, this is going to negative infinity. Or if you wanted to, you could draw it as a parabola. It's going to be an upside down parabola because of the -4. And as b goes to infinity, it's going to go to negative infinity. So this guy is going to negative infinity. So as b gets very large, this gets very large in magnitude, but more and more negative. And then as b approaches infinity here, this is going to be e to a very large negative power. E to a large negative power. Remember we did that e to the -1000? Remember we always do this. I do this a lot. That's 1 over e to the 1000th. That's 1 over something very large. This is very small. So this is very small. So what we have is a negative infinity times 0 indeterminate form. Now indeterminate forms can be handled by L'Hopital's rule, but you have to do a little bit of algebra first. You have to rewrite them. After you rewrite them, then we can apply L'Hopital's rule. So I need to write this as either 0 over 0 or plus or minus infinity over infinity so that I can apply L'Hopital's rule. I think the easiest way to do that is to take this e to the negative b over 4 and put it in the denominator and make it e to the positive b over 4. So this is equal to this. I think it might be time for some new Sharpies. This one that is acting up. And over here I just have a plus 64. All right. Is it infinity over infinity indeterminate form now? Well, it sure is. E to a large power is a large number, and then 4b squared, that's still a large number, times -1, so I have a negative infinity over infinity indeterminate form here. So I can apply L'Hopital's rule. That's nice. We always put an L over our equals sign when we apply L'Hopital's rule. Remember what L'Hopital's rule says? It says the limit of this is the same as the limit of this. You take the limit of, or the derivative of the numerator and the derivative of the denominator, and you're going to get the same answer. So the derivative of the numerator here is 8b plus 16. Derivative of the denominator is 1/4 e to the b over 4. So we're taking the limit of that and take that answer and add 64 because the limit of 64 is just 64. Is it still indeterminate? Yes, it is. I've got negative infinity over infinity again. If I wanted, I could flip that 4, put it up there, but it's still negative infinity over infinity. And put them in quotes because they're not numbers. It's just an indeterminate form. So we apply L'Hopital's rule again. Take the derivative of the numerator, take the derivative of the denominator. Now, is that indeterminate? I hope you said no, Miss Townsend, because that's a constant over something really large, and a constant over something really large is something really small. This thing is going to 0, and so our limit is 64. Okay, so we had to do some algebra. I had to do a little L'Hopital's rule here with the limits at the end because we had an infinity times 0 indeterminate form. But then we were able to show that as a function of b, the area under that curve is this. It's a complicated function of b. The area from 0 to b is given by this number. You tell me b is 1,000, I can plug in b is 1,000 right here, and it's going to give me the area. You say, well, what happens to that as b gets closer and closer and closer and closer to infinity? Well, it turns out This guy goes to 0, and we just end up with the 64. So we had 64 minus this thing. And this gets smaller and smaller as b goes to infinity, and the resulting area, net area, is 64. So this area under the curve, this area here, I'm going to call it area 1 minus area 2. In some limiting sense, this unbounded area 1 plus this fine bounded area 2, this minus that is 64. So our net area is 64 square units. What units? The same units you're using for the x and y axes. And this improper integral with infinite bounds converges.